This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
So while Francesco's setting up, he's a researcher scientist at IBM Quantum, at IBM Research Zurich, where he tries to split his time between equally quantum simulation and quantum machine learning. Actually, Francesco, you also sent me a fun fact and a useless superpower. So your fun fact is that his surname is in Italian means Turkey, which I guess around this time is rather dangerous. And his useless superpower is that he would like to be able to transform into any kind of food, see above. And today, Francesco is going to be talking about quantum neural network diagnostics with quantum tangent kernels, and you have the floor.
Thank you. Do you hear me well? Okay, cool. Thanks, Marco. Thanks to the organizers for having me here, and to all of you, please don't eat me. So the motivation for this work is a rather simple question. So why do quantum, or classical for that matter, neural networks compute a certain function? And notice that this is not the question about how do they compute this, because this we know quite well. Like, we know how the gates work, we know how classical neurons work. So we know the microscopic theory of neural networks in a way. And the question is instead, what is a macroscopic theory of this model? So this is basically the same relationship that we have between statistical mechanics and thermodynamics, just in reverse, that we figured out statistical mechanics first now, and we want to do thermodynamics of these models. And actually, I didn't come up with this question. It's something that is very well known already in the classical community. And this led to the development of what is known as effective theory of deep learning. And if you allow me to be a bit schematic, the question is all here. So a trained function from a neural network model is something that looks like this. So it's something that accepts inputs, which is the training data for which you want to do inference, for example. And it depends on some set of trained parameters. And if you want to check how these trained parameters depend on whatever you did at the initial point of your training, you can formally expand this into a Taylor series. So that you can express whatever you will compute at the end of your training as a function of some things that you already know at the beginning. Now, we have no particular reason of believing that this is going to be a simple problem to solve. In fact, we do need deep learning. But if you ask a physicist to solve this problem, which is very complex, the first thing they will do is to try to find a regime where this is very simple. So spherical cow in a vacuum kind of idea. And it turns out that the spherical cow in a vacuum for a classical neural network is a very wide model. Okay? When a classical neural network becomes very wide, everything becomes simple. And in particular, you can write exactly a solution for this set of trained parameters as a function of the initial parameters, the initial function, and the derivative of the initial function. And you need nothing else, so all higher order terms vanish. And a key object in this theory is this neural tangent kernel, which is basically playing what actually the first derivative of this model would be, and is something that will come up later on also in the quantum setting. The second thing that physicists will do, of course, is perturbation theory. So you have this highly unrealistic model, and then you try to perturb it away from the unrealistic conditions to see whether you can make it a bit more realistic. And for classical models, this has to do with perturbation theory in 1 over the width. And if you do it at first order, you will find that just a few more derivative terms come into the game. Okay, there is a bit of dependence on the learning algorithm and so on, but you can even write down a closed formula for a finite width neural network prediction that, according to the authors of this book, fits nicely on a t-shirt if you want. So how does this work in the quantum setting? Well, the things you can carry over most of the theory quite straightforwardly. For example, if you take a parameterized quantum circuit model and a quadratic loss function, you can just need to apply formally gradient descent with some learning rate eta. You assume that this learning rate is small enough. You linearize your model, and you find a definition of what a quantum neural tangent kernel would look like, which is basically just an adaptation of the definition of the classical version of it to a quantum model. And then you can go to your spherical cow regime. So you can assume that for whatever reason you are in a so-called lazy training regime, where this neural tangent kernel becomes constant. This is, for example, the case when the parameters of your training don't change too much, or there are a few other conditions that I will mention quickly later. But if this is the case, then the model essentially behaves as its linearization. And under these assumptions, you can, for example, prove that the residual training error will decay exponentially. So you have exponential convergence of your training, and you can prove this. Before you think that this solves all your problem, remember this is a spherical cow model, so still highly unrealistic. To get to this result in particular, you need, of course, a small learning rate, and I'll say a bit more on this later. But you need the QNTK, so the neural tangent kernel for this model, to be concentrated, so that essentially its value is fixed at whatever you had at initialization, and that the fluctuations of this guy are small. And to get to this, you can do a formal analysis, and you can see, for example, what the value of this like frozen quantum neural tangent kernel would be in this large depth and large model regime. And you will see that, okay, it's a number that depends on the number of layers that you have on the model, on the dimension of the Hilbert space of your model, and on the observable that you use to get your results out. And if you want really this decay rate to be of order 1, you need the number of layers to be very large. So typically equal to the dimension of the Hilbert space or the square of that. And this is showing clearly that this is a spherical cow. You can also go a little bit deeper and prove that the fluctuations are actually small, and the actual like higher order terms also vanish under certain conditions. You need very high randomness assumptions, and you can find all the details in these papers here. What we did next was like, okay, we know this theory a bit, still remaining in the spherical cow assumption. What is the other uses of the QNTK? Can we use it in practice to actually gain insights on some properties of the model, or can we use this in any way to guide the design of a model? And for that, we actually used this formula, which is something you can rederive from the same assumptions that I stated at the beginning. This basically tells you how the prediction of the quantum neural network model evolve in time under the frozen neural tangent kernel assumption. So you see this is mindful of the exponential convergence of the error. These are the training labels, and these are basically a transformation of the training data through the frozen neural tangent kernel. And if you apply this during training, you can get insights on, for example, what the training speed of your model will be, what is a good choice for the learning rate, and so on. And if instead then bring this to an infinite time, you can, for example, check what the predictions of your model will be. The important thing is that all of this you can evaluate at the beginning, so without doing any training. You can evaluate the neural tangent kernel under the assumption that this stays constant, and everything else is basically only depending on the training set. So a bit of a technical slide. You can write your things in a vector notation over the data set. The quantum neural tangent kernel is actually a matrix over the data set indices, so you can diagonalize it. You go into the orthogonal basis of this, and you can rewrite the training dynamics equation in a very simple way. And you can get a couple of results. One is that there is a critical learning rate that you should not exceed, and this depends on the inverse of the maximum eigenvalue of the quantum neural tangent kernel. And the other one is about what is the typical training decay time. This is conditioned on, let's say, the QNTK condition number. So it's a ratio between the maximum and the minimum eigenvalue. Then you can check what the predictions of your quantum neural network model would be if you were to fully train it. And it will not be surprising to anyone to see that, quantum neural networks, we know very well they are essentially kernel methods. The nice thing here is that this shows that in this large width limit, the quantum neural tangent kernel is the natural kernel of these models. And the natural features are these essentially derivatives of the outputs with respect to the parameters. Okay, yes, this is just a kernel prediction, so by definition you have exact predictions on all the training points, and the interesting thing is maybe to check what happens if you use this for points in the test set. Okay, this is all I have to say about rigorous results. Then we did a couple of numerical experiments to show how these things perform in real life, even without formally getting into this regime of the super idealized model. We did this for a couple of ansatses for a very simple classification like regression problem, predicting the magnetization of a 1D transfer field Ising model as a function of the field strength. And we used a couple of encoding strategies just to see a bit of the extremes. Like one is an encoding strategy that lets you access only very low frequencies, and the other one is one that has access to high frequencies in such a way that you can overfit if you want, so that we can see whether the quantum neural tangent kernel allows us to predict this overfitting behavior. And I mean, we confirmed through numerical simulations that many of the intuitions that we have from the theory of neural tangent kernel actually apply in real life. For example, if you increase the number of parameters, the minimum eigenvalue grows, so you have faster training. And certain models, for example, high frequency with Hamiltonian, with hardware efficient ansatz is expected to train faster than other models. If you increase the number of parameters, you also have let's say the training dynamics becomes faster. In particular, we predict from our neural tangent kernel theory that a certain family of models, that are the ones with high frequencies, would in fact overfit. These are the predictions that the quantum neural tangent kernel would do at initialization. And then we confirm this by actually training the models and showing that they in fact respect the things that we were predicting beforehand. So for example, that the high frequency models train faster and to a lower error, but that they also overfit. In particular, it was also nice to see that the predictions that you make with the quantum neural tangent kernel actually become closer and closer to the ones that you would obtain by training the actual quantum neural network, the more you are in this lazy training regime, so the less the parameters change during the training. This is just to show you an example of what this looks like. For example, in this high frequencies regime, you can see pretty well that you do overfit quite heavily to the training set. But the nice thing is that this red line is the prediction that you obtain from the neural tangent kernel. The blue line is what you would obtain by training the quantum neural network, and you see that they agree pretty well. Instead, for the low frequency regime, you're doing a bit better, and this is essentially what you would predict with this QNTK. With this, I thank you very much for your attention. Let me acknowledge all of my collaborators on this project, in particular Junyu from the University of Chicago, who did most of the heavy lifting on the first two papers, the more technical ones, and he basically introduced me to this beautiful world of effective theories for deep learning. And the more recent results, instead, we did them in collaboration with the University of Pavia and with Christ. Thank you.
Thank you very much, Francesco. I already see a question here in the front. Yes, by Alessandra.
Are you aware of a generalization of the neural tangent kernel, which is called the PAC kernel?
Yes. I think there was a paper by Michele Grossi and others on this idea, right?
Yeah. Is that do you think can be any?
I think it's interesting. It's an interesting.
Useful for this purpose also of your diagnostic.
Yes, I think it would be useful in this regime where you don't have this fixed kernel idea, and I guess the next natural step here is really to do perturbation theory on these models. We did a couple of these. Like this differential QNTK limit is basically the first order perturbation theory. It becomes very technical very quickly, so it's also a bit unpractical most of the times.
We have time for one more question. Here we have one in the front.
Sorry, so what motivated you to look at neurotangent kernels? Because classically their performance is not that great.
Just to understand how these models behave.
So do you have any particular
It's a theoretical physicist perspective of quantum neural networks.
I think we do have time for one more question. I see a hand in the back.
Thanks, Francesco. I wonder, I think I spoke with some of your co-authors on that. How could you give an intuition why are they good for shallow neural networks, quantum neural networks?
Sorry, I didn't get the last part.
The shallow quantum neural networks, the performance of QNTK on shallower models.
Empirically, we found that it works reasonably well, but we have not really investigated whether this is due to a particular feature of our model that we didn't, I don't think it's a general behavior, to be honest. It might very well be that we just chose lucky models for this.
I think we had one more question, but I intend to keep us on schedule with an iron fist. So let's save that for the coffee break, and let's thank Francesco again.